Hello and welcome. I'm Ariel Johnson from the Leakey Foundation, a nonprofit dedicated to supporting human evolution research and sharing discoveries. Today, we are rebroadcasting a throwback episode from 2020 featuring Dr. Hailay Reda, and I hope you enjoy it. Hailay is a recipient of the prestigious Baldwin Fellowship, and this year marks the 45th anniversary of the Leakey Foundation's Baldwin Fellowship Program, which has been fulfilling students' dreams of studying human evolution since 1978. This year, a record number of scholars have applied for assistance, and the need for meeting this growing demand and supporting the next generation of global leaders has never been greater. So I wanted to turn to my lunch break science friends for help. In honor of the 45th anniversary, all donations up to $4,500 will be matched. That doubles your impact. Your contributions, no matter how small, will make a significant difference in the lives of these talented students. Donate today and be part of their incredible journey. Now, I'll turn the floor over to the rebroadcast of Dr. Hailay Reda. My first question is, why are we interested in the environments of our early ancestors?
This is a very good question. Let me start with the modern environment. As we can see from this slide, the modern environment provides several resources to the animals living in that particular environment. So animals can find their food, they can find their drinking water, and they can also find their sleeping site, as well as the appropriate substrate on which they can move. So if there is a change in the environment, what this means is, in one way or another, they can be affected. The animals can be affected because of this change. So it is logical to assume that a similar situation might have happened in the early humans. So this graph is showing the environment of early humans in East Africa. So we see a general trend of increasing in an open environment. And studies have also provided evidences of appearance and disappearance of different early human species. So what this means is that early humans evolved in conjunction with the environmental changes where they lived. Not only the early humans, but also other faunas. So understanding the environment of early humans is providing us the bigger context to understand the evolution of early human ancestors. So, sorry, they have been affected by the environmental change, not only early human ancestors, but also other faunas, like the lineage of fossil monkeys were also being affected by this change. So since at about 4 million to the closer to 1 million, this lineage has adapted the environment by changing its morphology. There is a general increase in size. There is a general increase in the complexity of its tools. So it's becoming more complex so that it was able to adapt to the changing environment.
So obviously you're not hopping in a time machine and traveling, back to see what the environments were like, but how can you understand what the environment was like just looking at the fossil record?
Let me start again with the modern fauna. If we see fauna like in a park or in an open environment, different animals prefer different habitats or different environments. If you see the slide, in this slide, Colobus grazer is preferring a more wooded environment, whereas the one on the right, which is a baboon, is preferring an open environment. So this is what we really observe in the modern environment. So if we see our fauna, the fossil fauna, we have faunas which prefer different environments. Some of them prefer open environment like the baboon. Some of them prefer a wooded environment like the colobus monkey. So if we analyze the faunal abundance that we have, the fossil faunal abundance that we have, if most of the fauna prefer a wooded environment, so this means the environment where they lived was an environment dominantly covered by trees. On the other hand, if our fossil faunas predominantly show a preference of open environment, and this means that environment where this fossil faunas lived was dominantly an open environment. And there is a very particular example, as you can see in the next slide, that Aramis was dominated highly by colobine fossil monkeys. And colobines are commonly known that they prefer a wooded environment. So this suggests that Aramis was a wooded environment. So Aramis is the site where Ardipithecus ramidus was discovered. So indirectly, the environment for Ardipithecus ramidus, commonly known as Ardi, was a wooded environment, an environment that was highly covered by big trees. So this is one way to understand the environment of early times, or the environment by the time where our early ancestors lived. And we also have another mechanism, like using isotope analysis. For this, the assumption is that different plants follow different photosynthesis pathway. What this means is that they have different mechanisms to produce their food. So big trees follow a C3 photosynthetic pathway, whereas grasses and grass-related families follow a C4 photosynthetic pathway. So animals eating on fruits and leaves show a C3 isotopic signature, or a C3 isotope. And animals that dominantly depend for their food on C4 grasses show their isotopic signature, C4 isotopic signature. So if we have fossil faunas that show more of a C3 isotopic signature, what this means is that their diet was dominantly fruits or leaves. And in turn, this suggested that the environment where they lived was highly dominated by a tree cover. On the other hand, if the fossil fauna that we have show predominantly C4 isotope signature, what this means is that they were highly dependent for their diet on C4 grasses. And this indirectly suggests that the environment where this fossil fauna lived was mainly an open environment. So this is the way we are able to understand ancient environments. But there are also other ways, other mechanisms, like pollen analysis, and also phytolysis and isotopic signature of paleosol carbonates. So there are different mechanisms to understand the environment of early humans, or the environment of ancient time in general.
So when you're collecting fossils for the faunal analysis, how much of the identification are you actually doing in the field?
In the first place, before I say the how much identification that we do in the field, I would like to say what are the fossil faunas look like that we find in the field. So mostly the fossil faunas are isolated tooth, because they are highly resistant to destruction in the process of fossilization. So crania and other complete skeletal remains are very rare. So the reason why I brought this slide is just to increase visibility of the specimens, because tooth or teeth are very tiny, so people might have difficulty of observing the important features. Otherwise, the composition of fossils that we have is mainly dominated by isolated tools. So coming to the identification, in the field, we tentatively identify specimens. because the field is mostly done within a short period of time. So there are a lot of rushes like doing other stuff too, not only identification. So tentative identification was mainly emphasized. So the identification mainly done at higher taxonomic level, not the lowest possible taxonomic identification. So here is the way we follow to identify fossil specimens in the field. For instance, this is a cast for a fossil monkey. So this represents a Sarcoptocine. Generally, we have fossil monkeys are broadly grouped into Sarcoptocines and Colobines. So this is a specimen of Sarcoptocine, and it has a relatively longer snout, and it has a very relatively narrow interorbital braids. And we also have important dental or tooth morphology that enable us to identify whether the specimen is a Sarcoptocine or a Colobine. In the first place, if you see the front teeth, they are relatively larger. And the molars are the teeth towards the back of our jaw. So if you see this bumpy-like structures, we technically call cusps. They are having low cusp relief compared to from the level of the gorge-like structure. So they are not very prominent cusps. And if you see the ridge that connects the cusps side to side, it is not very, very sharp. On the other side, on the other hand, if you see on the lateral, on the side, you see a little bit of narrowing the cusps towards each other. So these cusps are becoming relatively closer. So what this means is that the tooth is forming a basal flaring, which means very relatively broad at the bottom and narrower at the top. For Colobines, this is of course relatively smaller size specimen, but they have generally smaller snouts, and this pillar, the interorbital pillar, is relatively broad. When it comes to their dentition, if we see the front teeth, they have very narrow and smaller incisors or front teeth. Coming to the molars, the back teeth, the cusps are prominently high. There is a high cusp relief. They are very sharp and high. And the crust connecting the cusps is relatively sharp. And when we see on the side, unlike the Sarcoptocines, they show like a straight-sided. So what this means is the proximity of the tip of the cusps is not very close compared to Sarcoptocines. So based on this, I'll give you a mystery specimen so that you can identify whether this specimen is a Colobine or a Sarcoptocine, like what we do in the field.
So it's time to bust out your new tooth identification skills. For those of you viewing live in the audience, you will look for the 3 features that Hailay just taught us and tell us your assessment of what it is. Is the mystery tooth a Colobine tooth or a Sarcopithecine tooth? Please post your identification in the comments now, and Hailay will go over the differences one last time as we're waiting for responses to come in. Do you want to put the tooth back up just for a few more moments, just so we can? Yeah, perfect. you want to review some of the features to help our audience guess?
Yeah, the ridge that connects the two cuspes and the height of the cuspes, the cusp relief, and the proximity of the cuspes, how close they are to each other. The cuspes placed side to side, and we have also an incisor here, so we can also talk about the size of the incisor, and yeah, flaring cusp height and ridge connecting the cuspes and the incisor size.
Oh, we're starting to get some of the assessments in. We have 1 vote for Columbine. Do we have some more? We have another vote for Columbine. Ah, a Cercopithecine. Another Cercopithecine. So, what is the correct answer for our mystery fossil?
Yeah, this is a Cercopithecine. We can go over the features again. Generally, this incisor is slightly larger than the Columbines, and when we see the cusp height, it's not very high like the feature we see in Columbines. It's slightly larger than the other specimen of Cercopithecine, but still it's low. And when we see the ridge connecting the two cuspes placed side by side, it's not very sharp. And there is also a slight tilting of this cusp, so there is some sort of becoming proximity of the tip of the cuspes. So based on this specimen is Cercopithecine.
So after the initial assessment, what does it take to confidently assess one individual fossil?
This is, as I have tried to mention earlier, what we do in the field in terms of identification is very tentative. There are reasons for this, because one of the important reasons is time. We don't have so much time in the field to do the detailed identification, and we don't also have other materials to compare with. So most of the activities are like surveying, understanding the geology, so identifying the potentials of fossil sites. So these are the most important things. But the detailed study is usually done in the lab, because we have relatively sufficient time for making a comparison of different specimens that have been already published by other scholars. So we pull out other comparative materials and we lay them out on the table, and we can compare their features against the specimen that we have. So the confident identification is done in the lab.
So we just learned to identify fossil monkeys, and your doctoral thesis project is on fossil monkeys. Why is it that we are interested in fossil monkeys as opposed to other animals? Yeah.
Yeah, there are a number of reasons that I can say. In the first place, if we see the modern monkeys, they are widely distributed in a very broad geographical location. We find them in a very range latitudinal differences. We find them in the tropics, we find them in the temperate areas, and also we find them in a different altitudinal differences. Some of them are present at lowlands, some of them are present at highlands, like the Chelada baboon in Ethiopia, which is living in a very mountainous area. And in terms of their climatic zone distribution, we find them in the tropical rainforest, we find them in the savanna environment, we also find them in the desert. So what this means is we have a chance to understand the modern analog so that we can compare with our fossil monkey faunas. And the other reason is they are, of course, relatively closer in terms of phylogenetic relationship to to humans. And not only this, fossil monkeys are very abundant in the fossil record in many sites, including Oranjomile, where I'm doing my dissertation project. So there are good sources of information to understand early human evolution and also to understand the evolution of this fauna themselves. And if we see, according to some studies, they have both early humans and old-world fossil monkeys started to expand their dietary adaptation at about similar time. So what this means is they adapted to a changing environment in a similar fashion. And there are also studies that show that early humans and fossil monkeys compete for a similar or consume at least a similar type of diet. For instance, Paranthropus boisei and Australopithecus lineage. And the other important point to mention here is monkeys have been used for decades as an important model to understand the evolution of early humans. And they are also being used to understand the paleo environment. Like I have mentioned earlier, colobine, because of the high abundance of colobines at Aramis, people argue that that area where Ardipithecus ramidus lived was mainly a wooded environment. So there are a bunch of reasons why this faunal group are very important to understand evolution and environment of early humans.
I am really excited for this next part because I really love the way you frame your current research project. Could you tell us about what you've got going on right now?
Yeah, let me start with the title of my project. It is Paleoecological Reconstruction of Early Humans at Oranjomile using fossil monkeys. So that's the title of the dissertation project that I'm working on. So Oranjomile is located in the northeastern part of Ethiopia, very close to other famous research sites. Compared to the other sites, it's located a bit north, a bit north compared to other sites. So when we see the contribution of these sites, as you can see in the next slide, as you can see in this slide, sorry, we have different important early human remains that are discovered from Hadar, like for instance, Lucy, and we have also other human remains discovered from Maka, Middle Awash, and we have also another important baby early human remain, which was discovered from the Kika, and the name of this human remains is Salam. And we also have Kadanumo, that's another important early human remains discovered from Oranjomile at about 3.57 million years ago. So what this all individuals tells us that they belong to one species. So it looks like there was an assumption that between 3.6 to 3 million years ago, there was only a single species of early humans in the upper region. However, this was challenged due to the discovery of other specimens from Oranjomile. For instance, an important discovery was announced in 2012 to show that there was a specimen, a partial foot specimen, mainly called the Burtele foot. So this specimen is not well affiliated with a specific taxonomic species, but it has a very important information in terms of understanding the bipedal locomotion. So I have included a footprint which is reported from Laetoli, and this tells us that there was a sort of bipedal locomotion closer to humans, not exactly like humans, but like closer to human way of moving on two legs. But what this partial foot tells us that there was at least there was a multiple of bipedal locomotion at about 3.6 to 3 million time range. Actually, this was discovered from 3.4 million fossil horizon. So this is very important because it tells us the presence of multiple bipedal locomotion. And later discovery also suggested that there was really additional early human species in the upper region. And this was also discovered from Oransomile from 3.3 million years ago. And the taxonomic or the species name for this group of specimens is Australopithecus deiremeda. So overall, we have Australopithecus afarensis, and we also have Australopithecus deiremeda, and this means we have at least more than one early human species in the upper region. So the there is clear that based on these discoveries, there was a diverse hominin species at or early human species at Oransomile, but not in the other areas. Although they are geographically closer, although they are relatively or contemporaneous in terms of their geological age. So this triggers a very important ecological question. Was there the environment of Oransomile, especially at 3.5 to 3.3 million, distinctive? Was what the Oransomile distinctive in its environment compared to other sites which are very close to Oransomile? So this was why I want to investigate. So for this, I picked fossil monkeys for the reasons that I have mentioned earlier. And I have framed on a method how to address the research question. So the first thing is I'll describe what's out there and identify or how many fossil monkey species do we have at Oransomile in that time range. And I will also understand the relative abundance and compare the sites. Is Oransomile having high abundance of a certain species of fossil monkeys compared to the fossil monkeys present at other sites like Hadar, Dikika, Maka? And I will also have a method to understand the diet of these fossil monkeys. One is understanding their dental functional morphology, or correlating the diet and the dental indices or the tooth measurement. So I'll able to know which one is having a more predictive power to understand the type of diet that they were eating. And the other method is isotopic method. So isotopic method is extracting isotop or understanding isotope signatures from their tooth enamel, so that understand what actually those fossil faunas were eating, so that comparing the different sites, if the fossil faunas at Oransomile were more of a C3 eater or a C4 eater compared to other sites.
Well, thank you so much, Hailay. We'll have to have you back when you get your research results. Now we have some questions from the audience for you. I know we have one. Why did Hailay decide to pursue this special area of study?
I think the first thing is I have seen the importance of fossil monkeys in understanding the evolution of early human ancestors. Of course, I have done my master's thesis on pigs, but when I see the relatively closer phylogenetic proximity of fossil monkeys to hominins, that gives me more comfort to work on fossil primates, so that I can clearly understand how humans evolve over time. So that's one important reason. And of course, the other reasons I have mentioned earlier are also important, because fossil monkeys are important in several ways.
Do we have, oh, here we go. How can we apply the past paleo-environmental information and knowledge to rehabilitate and restore the current degraded ecosystem?
That's a very broad question, and I'm not very sure to say this ways, but there are some important lessons that we can take from the previous environment. We have seen that, as I have tried to display in one of my slide, environments have been changing over time. So so we can get a lesson that the current environment is of course changing, but it will also continue to change. But I don't really know the exact way of taking or using that for a rehabilitation of this environment.
Yeah, and I feel like also, you know, environments do change over time, so it may not make the most sense to try to return an environment to the way it was. Do we have another question? Oh, how can carbonate help us to reconstruct past environments?
For this, I'm not exactly doing on carbonates, but the the way we use them is in a similar approach that we use understanding paleo environment from to enamel. So the carbonates are produced from the plant remains over time. So the plants could be big trees or grasses, so that the isotope signature that we get from this paleosoil carbonates tells us that the type of plants that were present at a certain area in a certain in a specific time.
So I think we have one more question. Is there any evidence that the monkeys were consumed by these hominin species?
That's a very interesting question, and I have been discussing this with my advisor. There are some, I think, from Oler Gasale, there was some cut mark or human-touched mark on a monkey skull. So there is an assumption that early human ancestors might have been eating monkeys, but there is no very intensive. So far I know, there is no very intensive research that shows early human ancestors were in some part dependent for their food on monkeys.
Now we're almost out of time, but I do have one final question for you. If you could answer it somewhat quickly. You have another really strong passion for building the facilities for studying human evolution in Ethiopia. Could you talk a little bit about that passion?
Yeah, that's a very good question, a little bit away from the research side. So there is one important thing, that Ethiopia is one of the countries being rivaled by very few countries in terms of the potential to provide the understanding of early human evolution. But when we see the contribution or the involvement of research in Ethiopian institution, is very minimal. There are, of course, some famous Ethiopian scholars who are working hard in this area, but coming to the involvement of Ethiopian institutions is very limited. So I have an interest to at least to build capacity in one of the institutions, mainly the already established institution at Mali University, which is dedicated to or established to work on human evolution and understanding of the paleo environment, or the environment of early human ancestors. So I'm really interested to build the capacity of that institution and have a better involvement of that institution and do research in human evolution and paleo environment.
Well, Hailay, I'm so happy that you could join us today. We want to really thank you. This was a really fascinating talk.
Thank you for having me.
Thank you so much for watching this broadcast along with me. We return to new episodes next month, so be sure to subscribe and follow the Leakey Foundation so you're the first to hear about updates and all of our upcoming episodes. So thank you so much for taking a break from your day and feeding your brain with the Leakey Foundation. Until next time, stay hungry for knowledge. Lunch Break Science is brought to you by the Leakey Foundation and made possible by the generous support of the Ann and Gordon Getty Foundation, Camilla and George Smith, and the Joan and Arnold Travis Education Fund, as well as viewers like you. Show your support of Lunch Break Science by subscribing, giving us a thumbs up, sharing, and making a donation to help create new content. In celebration of the 45th anniversary of the Leakey Foundation's Baldwin Fellowship Program, all donations will be doubled until we reach our goal of $4,500. Still craving science and can't wait till the next episode? You can feast on the Leakey Foundation's content library with past episodes, lectures, our podcast, origin stories, and much more. Thank you for tuning in, and see you next time.